Hi, my name is Ian Mars, and I am a master's student here at IUPUI. I'm studying geology, and I work in the experimental geochemistry lab. My research involves meteor impacts. In 2013, there was a meteor that exploded over Russia. It was sort of a popular thing on the internet for a while because all these dash cam footage videos came out, and there was this huge fireball streaking across the sky. Over 1,000 people were injured. These are dangerous scenarios. If there is going to be an impact, I think it's a very good idea that we know what happens when one hits the Earth. But also, the Earth isn't the only place humans will be. In just a few short years, in 2024, the NASA Artemis mission is going to take people to the moon again. The end goal, the next step after the Artemis mission, is to use the moon as a stepping stone to get to Mars. Those surfaces are, in some cases, entirely made of craters, and we should have a good idea, a good understanding of what impacts do to a surface so that we can survive on the moon and Mars to the best of our ability. So if we had something like a piece of volcanic rock and it was impacted by a meteor, sometimes what forms are these. They're these things called tektites. What I do is we synthesize synthetic tektites. So we take powder, so we powder up a rock, and then we shoot it with a laser. We heat it up to very high temperatures to sort of simulate that impact. And that tells us a lot about what happens in the initial stages of an impact that are really hard to understand for us humans because they happen so fast and they deal with such high temperatures and pressures. Well, what we're hoping to find is an answer to sort of the mystery of meteor impacts, and that mystery is, why are these things, these tektites, why are they so rare? There are 190 confirmed impacts on the Earth right now that we know where the craters are. Only 4 of them have made tektites, and so that's clearly not a lot. These products are essentially eyewitnesses to an impact. This was there when the meteor impacted. And so it can tell us what was the temperature like, what was the pressure like, what was the soil made of at the time of the impact. And that's really what we're hoping to figure out with the research is, how do these things form exactly? Why do they form, and why do they form so rarely?
Hi everybody, it's Ian again. I just wanted to interrupt and give you a little background on me, tell you about why I became a geologist. So in high school, I had an earth science class that I really enjoyed. I thought it was very cool. A lot of interesting stuff there, but it didn't click to me then that that's what I would want to do for the rest of my life. So when I came to college, I started out in a degree that had me designing video games. That was something I was interested in. I said, hey, I'll give it a shot. Turns out I wasn't very good at it, so I ended up transitioning out, and I tried a few things. I learned a bit more about myself, and what I found out was that what I wanted to learn about and read about and study and talk about all day was planets and space. But I didn't quite want to go astronomy and study the planets that way, so I had to find a different way. And so what I did is I talked to some professors and I asked them how I could study other planets, other solar systems without having to do the astronomy that I wasn't very interested in. What they told me was, hey, why don't you try geology? So I tried it out. Turns out I really liked it. I liked the geology classes I took, so I took more of them. Eventually, I asked one of my professors, the person who I'm working for right now, I'm working in their lab, I asked them, do you have any jobs for me in the lab? Is there anything I can do? They said yes. It was an easy job at first, but then I got better at it. The jobs got a little harder, but they also got more interesting, and that continued. Harder jobs, more interesting jobs, and it kept going, and it kept going, all through my undergraduate degree, and then eventually I got to the point where I started my master's. I started working in the lab here as a master's student, and I want to take that, and I want to continue on and keep doing that for the rest of my career. So what I want to do now is I want to talk to you a little bit more about specifically what do I do in the lab. So remember, here in the lab, what we do is we take a crushed up rock, we put it in our furnace, We shoot it with a laser, and what we end up with is a tiny, tiny, tiny little glass sphere. It's just a few millimeters across. It's very small. And what we want to do with that sphere is we want to look inside of it, because on the inside, it holds clues about the meteor impact that we're trying to simulate. And so to cut it in half, we need a special saw. And what we have to do is take the sphere and we put it underneath a wire, and the wire will move back and forth. But in order to cut through the rock correctly, we need to mix up a slurry. And what a slurry does is just sort of greases the inside of the sphere. It allows us to cut through the sphere easier. So we mix up the slurry, we put it on the machine saws back and forth and back and forth and back and forth with its wire, and eventually it'll cut all the way through the sphere, and the sphere will be in two halves. Since the sphere is so small, we need a special microscope to look at it. We take that sphere, that half of a sphere, we put it inside our powerful microscope. It's called a scanning electron microscope, and it lets us see incredibly close to the sphere. And it makes these beautiful pictures that you're seeing here. And what these pictures tell us, it tells us about what does the glass look like on the inside. Is it all glass? Are there some big crystals? What's going on in there? If there are crystals, what are they made of? And again, all of these things that we're learning about with the microscope are clues. They're clues about the meteor impact that we're simulating. And that's what we do here in the lab.
My name is Leah Wood, and I am a PhD student in Earth Sciences at IUPUI in Dr. Gabe Filippelli's lab. I never thought in a million years that I would ever want to be a scientist. I was really bad at math in school, and because of that, I wasn't so great at science either. And I wanted to be an elementary teacher. And so I was studying elementary education during my bachelor's degree when I first went to college. And I was required to take one single science class. And I picked geology. Don't know why, just for fun. But it turned out to be a lucky thing. I really, really loved geology. And my professor tried to convince me to go ahead and change my major to geology right then and there. But I really wanted to be a teacher. So I stuck to my guns and I got my degree in elementary education, and I became a sixth grade teacher. After a few years of teaching, even though I loved teaching and I loved the kids, I decided I needed a change. I wanted a job that would allow me to travel and allow me to play outside a little more. And I remembered that geology class that I enjoyed so much my freshman year of college. So kind of crazy, completely on a whim, I decided to quit teaching and go back to school. I went back to Ball State University to get my master's degree in geology. So during my master's degree, I was required to do a research project and write a thesis. And my topic for my research was the effects of climate change on the availability of drinking water in Nepal. Nepal is where you find Mount Everest, which is the highest mountain in the entire world, and people travel from all over the world to go see and climb Mount Everest and see the beautiful Himalayan mountains. But the Mount Everest region of Nepal isn't just a tourist area. There are several thousand people who live there too in the remote mountain villages, and they live there year-round. And they don't actually have city water supply like we have here in the United States. And they don't have drinking water wells either. They rely on river water for their drinking water and all their domestic water needs. Cooking, drinking, bathing, washing, all of it. They get the water from springs and from the river. But the river water comes from a combination of rain and snow and glacier melt. Well, you've probably heard of climate change and probably know that the world is getting warmer. What that means in the snow-capped mountains of Nepal is that the glaciers in the snowpack are melting. They're supposed to melt a little bit every summer, and that's where people get their drinking water from. That's how it winds up in the river in the first place. But what's happening because of climate change and because of global warming is that the glaciers are melting faster than they can be replenished every year. So for my master's project, I went to Nepal for 3 weeks and I collected water samples from all over that region of the country. And I brought them back to my lab at Ball State University, and I used isotopic geochemistry to determine how much of the water came from glaciers and how much of the water came from other sources like rain. I realized that the glacial melt and the snow melt had more of the lighter isotopes of oxygen in them, and the rainwater and the rest of the river water had more of the heavy isotopes in them. So when I took these water samples from the rivers and springs in Nepal and I brought them back to the lab, I can look at the ratio of light to heavy oxygen isotopes in those samples, and I can determine roughly how much of the water came from a frozen glacier or from frozen snow and how much of it came from rain. I discovered that like 2/3 of the drinking water during the dry season came from snow melt. So the purpose of my research was to allow the people of Nepal to plan and anticipate the effects of climate change on their drinking water supply. And if they're able to plan, then they can be more resilient to the effects of climate change. You're probably wondering what drinking water has to do with geology or with earth sciences. Because when most people think of geology, they think of rocks. Well, there's more to geology and more to earth science than just rocks. In fact, earth science involves the study of all non-living components of the earth system, which includes the hydrologic cycle and water. It also includes things like atmospheric processes and the climate, and it involves soil as well, even the soil under our feet. And in fact, soil would wind up being an important aspect of what I do now as a PhD student. Here at IUPUI and Dr. Filippelli's lab, we study environmental lead contamination and its effects on public health. Lead is a naturally occurring element, but it's also, unfortunately, a powerful neurotoxin, and it has a whole slew of negative health effects. Throughout the 20th century, lead was used as an additive in paint and in gasoline. It was used to make paint more flexible and durable, and it was used in gasoline to make engines run more efficiently. And the result of that has been that there is lead in the environment around us, in the soil, and even sometimes in the dust in our homes. So what we do in my lab is we try to prevent people from being exposed to lead in the environment. And the way we do that is we provide people with lead testing kits so they can take this kit home and they can provide us with samples of their water, their household dust, and the soil around their house. And we analyze that and we tell people if they have elevated levels of lead in their home. So kind of like my research in Nepal allowed people in the mountainous regions around Mount Everest to be able to plan for the effects of climate change, the work that I do now, these kits allow people, knowledge is power, allows people to protect themselves and to live safely with lead. We connect people with resources and skills that they need to limit their exposure to lead in the environment. I love my job. It was a very good decision to go back to school and decide to be a scientist and be a geologist. Remember, what I really wanted was to be able to play outside and to travel. Well, since I started studying geology, I have been to Nepal, Zambia, Canada, and I've been all over the United States. It's really been just a huge adventure. And it's also been really rewarding because I get to help people. And I don't think I really thought about that when I was in science class in middle school or high school. I didn't think about how much science is used to help people. You might also be wondering, wait a minute, I thought she said she's bad at math. How is she a scientist now? Well, I was really afraid of math when I was in middle school and high school, but once I went to grad school and started my master's degree and now my PhD, I found that math wasn't so scary anymore because I was learning it, not because somebody said I had to, but because it was necessary for something that I was passionate about. And it really wasn't so bad. So I'm not bad at math anymore. Ultimately, I just want you to know that if you hate math, or if you're bad at math, or if you're just scared of math, don't let that stop you from an interest or a passion for science. You can definitely overcome the math thing, I promise.
Hi, I'm Matthew Lanning. I'm a PhD candidate in the Department of Earth Sciences here at IUPUI. I work with Dr. Lishan Wang in the Ecohydrology lab. Ecohydrology is kind of a unique field in earth sciences. So as you can tell from the name, it combines ecology, eco, with hydrology, the study of water and the water cycle. And this is particularly fun for me because I'm not really an earth scientist in how you would usually think of it. I'd never studied geology or anything like that. My background is in biology and environmental science. So I got to take my love of ecology and mix it with the really cool processes that happen in the hydrological cycle. For me specifically, I study forested ecosystems and how large-scale things like acid rain impact how they use their water resources. What we do in our research is we look at how those two processes interact with each other. Acid rain affects the soil chemistry that trees grow in. It leaches out nutrients that plants would be needing. And without those nutrients, plants have to invest more water resources to pull up the nutrients that they need. That's how they get them. And so for us, we are interested in how much more water they have to use under acidified conditions versus non-acidified conditions, because we're interested in a parameter called water use efficiency. And water use efficiency is just a metric of how much carbon dioxide plants take in relative to the amount of water they have to spend to get it. And so our research seems to suggest that as acid deposition increases, water use efficiency in most species anyways tends to decrease quite a bit. The way we study plant water use efficiency back into the past is by combining a cool mix of different tool sets. So the first that we use is dendrochronology, or the use of trees to look back into the past, back in time. And so if you've ever seen a tree cut down or looked at a branch or something, you'll know that there's tree rings inside of them. You can count them and figure out how old the plant is. Well, we can do the same thing with the plant's chemistry. We can go back in time and look at some chemical markers in the tree rings and figure out what they were doing. Trees don't just sit there passively. They record information like temperature, humidity, where their water comes from, how much they're using, how much CO2 they took in. And the way we translate that chemical information into things that us humans can use is through stable isotopes, another toolkit. So stable isotopes are just like any other element. So we can take carbon as an example. The element carbon is defined because it has 6 protons, and it also has 6 neutrons in its normal variant. A different flavor of it, carbon-13, has 1 extra neutron. So it reacts with things a little bit slower because it's a bit heavier, and because of that difference, the plants utilize it in different amounts from the normal variant, carbon-12, and we can figure out, based on the relative amounts of those two inside of the plant, how much carbon dioxide it used, and how much water it let go at the same period of time. Alright, so I often get asked how we can sample a few hundred trees for any of our studies and not kill an entire forest when we go out to take our samples. And the answer to that is this little tool here. This is an increment borer, and we keep this tiny little rod in our backpacks when we go hiking, and it disassembles into a fully functional tree sampling device. So it's really simple how it works. we take this end, which is sharp and pointed, and it's hollow, and drill it into the tree, leaving just a little bit out. Once we have the increment borer fully inside of the trunk of the tree, we can use this little extractor at the end to pull out the sample. We take this part back to the lab with us for analysis, and we leave the tree with just a tiny little hole on the outside that it can patch up later. It really doesn't damage the tree at all. They're mostly dead on the inside anyways. It's not a particularly long story, but when I was, I think I started in about 8th grade or so, I took a job with the town that I lived in to go out into the woods and build trails and boardwalks and paths for people to walk on. And the longer I stayed at that job, the more and more people I interacted with, and the more I became curious about what actually was going on outside of the trails that we were building. And so I started to spend some time with the naturalist we had at the site. He taught me all the names of the trees that I pointed at, and all the different medicinal and edible plants that were out there, because those were interesting to me at the time. And I asked him how he got this job and how he got to do such cool things all the time. And it turns out he went to school for ecology and biology. And so the more and more I looked into that, I learned that there's many fields of research, and I signed up for an undergraduate degree in biology and environmental science, and just tried to learn as much as I possibly could while I was there. Whatever class sounded interesting, no matter how crazy it was, I always went and did it and tried to take even just little bits away from it that I found super interesting. And when it came time for me to graduate, I realized that my 4 years in undergraduate were not enough. I wanted to do more, and I wanted to contribute some of the text that you read in your textbooks someday, if I may be so crazy to do that. And so I signed up for originally a master's degree here, and later a PhD, just in projects that I found to be just crazy interesting. They're things that I just constantly wonder about and I never really put down.